Okay, so this time we're going to have a look at a sort of clearer interpretation of imaginary points. We're also going to define imaginary lines, and we're going to look at a conic in a more kind of complete way, embracing the complex structure that it has. So firstly, let's just recall this so-called growth measure induced upon a line by a conic with a pair of points O and O'. Such a growth measure is also known as a hyperbolic projectivity from a line to itself. That's the more modern name for this sort of mapping. So this is going to build on what we've done over the last couple of videos on imaginary points and imaginary lines and the complex part of a conic. So let's continue then. We'll recall this sort of growth measure projectivity. So we start with a point on the line, and then we connect it on a black line, and we connect it by a purple line through O' and see where that line meets the conic at the second point, and then we connect that point back to O, and this gives us a point on the line again, and we can think of that as the image of the initial point under this projectivity. And the idea is we can imagine repeating this process again and again if we like. So this initial point gets mapped to the left, that point gets mapped further to the left, and we can see in this system that the fixed points, there's an attractive fixed point on the left, and there's a repulsive fixed point to the right. So the fixed points are where the conic makes contact with the line. Now, notice that these are the fixed points for any positioning of O and O'. So moving O and O' changes the nature of the mapping, but it doesn't change the nature of the fixed points. They're always where the conic meets the line. Now let's have a look at the case where, so we could define the fixed points if we liked as the points where every single kind of dynamics induced by this circle with any two different positions of O and O', well, the common fixed points of all of those dynamics, they're the contact points of this line and this conic. Now that's not especially sensible, because there's much simpler ways to think of the definition of where a line meets a conic in this case. But if we move the line down so that the conic and the line have no real points in common anymore, well, that notion still holds. So for any positions of O and O', we now have a so-called circling measure induced upon this line, corresponding to sort of, well, it corresponds to the motion induced by looking at how a line rotating about some point on the plane, some special point on the plane, is pointing at this black line. I'll show you that again in a minute. But the point here is that this kind of circling measure mapping of the line to itself, which happens when we have a similar setup but the black line doesn't meet the circle at real points, well, now that this system has no real fixed points, this mapping, things are always getting sent to the right in this case. But as we were saying before, this system does have complex fixed points, which some authors call imaginary fixed points, and we can find them by the constructions we were looking at before. And just as in the previous case, moving O and O' will change the nature of the dynamics. We could even reverse the direction of the motion, but it won't change the nature of the imaginary fixed points of this system. So for this reason then, we are going to have a look at a way we can interpret these imaginary fixed points in this context. You see, they're the fixed point of any of these mappings. So what we're going to do is choose a specific mapping called an involution, which has particularly nice properties, and then we can essentially pair up these imaginary fixed points with involutions. So we can sort of think of these imaginary points as involutions. So what we're going to do is move O and O' in such a way that we have a period 2 mapping. So if you have a look at this black line you get by following 2 arrows away from our light blue image, watch how that changes as we move O'. It goes off the left of the screen, and at this point here we actually have a period 2 mapping. So a period 2 projectivity, that's precisely what a involution is. That's a definition of an involution. And you can see here that it's not just one point that's returning to itself. Every single point on the line now is getting mapped to itself. They're all in this period 2 orbit. Applying this map twice to the line returns every point to its previous position. So it's an interesting question to ask. What are the special positions of O and O' which induce an involution? So it turns out that, okay, let me just remind you of something. Say we have a point somewhere, I'll put it on this black line for the sake of simplicity, but it doesn't have to be there. If we want to work out the polar of that line with respect to this conic, we draw tangents to it. And now, if we find where these tangents meet the conic, then joining those contact points up, which I shall do with an orange line, that orange line is then the so-called polar of this point on the line. Now it turns out that the condition, so also let's say we want to work out the point for which this black line is the polar. Well, such a point is called the pole of the black line. So let's work out what that is. Well, it turns out that if we work out the polar of another point on the black line, then there's a result that says that the place where the polars of 2 points on a line meet is going to be the pole of that line. So in other words, the place where these 2 orange lines meet is the pole of the black line. And this special black point here, this pole, has this property that if we take the polar of this point, we get the initial black line back again. Now it turns out that the condition that O and O' have to satisfy to induce an involution is that the line in between them should go through the pole of the black line. So in order for O and O' on a conic to induce an involution, the line through O and O' should go through the pole of a black line, of which the involution is induced upon. So that's that. Okay, so it turns out that there's actually a much easier way to construct this involution of this black line to itself with respect to the conic. And what that is if we have a point on our black line and we want to determine its image under the involution, all we have to do is take its polar and find out where that polar line meets our initial black line again. And that, in fact, is going to be the image of our initial point under this involution. So this is a much easier way to obtain the involution than doing all that construction with O and O dash. And it's easy to check by taking the polar again that this is indeed a period 2 mapping. Okay, so let's have a look again at this case where the line meets the conic at real points. So this is an involution, and we can think of it as defined by polarities, as I was just saying, or as I began discussing the video discussing, we can think of it as induced by positionings of O and O dash. So this particular mapping from the line to itself is essentially growth measure dynamics. The modern name for such a mapping is it's a hyperbolic projectivity. In fact, this has a more specialised name, it's a hyperbolic involution, because it's an involution this time. Now, obviously the fixed points of this involution, as I've said before, are where the line meets the conic. Now let's shift the line so it has no real points in common with the conic. Now this is circling measure dynamics. The more modern name for this is it's a so-called elliptic projectivity. In fact, it's an elliptic involution because it has period 2. And the fixed points of this involution are the places where the line meets the conic, the complex contact points. How do we find them? Well, we can find them by the previous construction, but we can also find them directly by looking at this involution. So to do this, well, we already have one point in its image. Let's pick another point and determine its image. Now it turns out for these kind of elliptic involutions, which are the ones that we're interested in, because they have special connections with complex points, well, it turns out that if we want to, well, such a thing, as I was saying before, it corresponds to the sort of motion induced by the rotation about a point. So we can find where that point is, and there's a rather interesting way of doing this. If we draw a semicircle from one point to its image, connecting one point with its image, and we do the same with another point in its image, these two semicircles will meet at precisely this place where this point here, this black point, such that rotation about this black point corresponds precisely to these dynamics. So if we draw some lines now, maybe segments is better, less messy. So if we draw a segment linking a point with its image, we can see that under this mapping, a point is just moved by a 90-degree rotation about this place here. I'll actually colour this point in. Let's colour it in green. So it now turns out that this involution we have induced upon the line, it corresponds precisely to a 90-degree rotation about this green point. I'll use full lines because they seem a bit more stable. Perhaps not. Well, anyway, it is the case that the involution can be thought of in these terms. And so you can see that, in fact, because any line is returned to itself once it's turned around 180 degrees, this is consistent, because rotating twice by 90 degrees about this point returns a line to itself, and therefore returns the place where that line meets the black line to itself. Now that we have this point here, that this involution corresponds to a 90-degree rotation about, we can use it together with the theory of how, once you've found the centre of rotation that induces a circling measure dynamic or elliptic projectivity, well, once you've found that point, we can use the theory that we've been discussing before in the first two lectures to work out the details of the complex fixed points of these dynamics, aka the complex contact point of this conic with this line. And the way we do this is just to draw out 45-degree lines from this green point here. So let's just clean up this picture. Excuse me. So that circle I drew, that was just for construction purposes, because now these 2 points that I've just made, they're going to be at 45-degree angles from our centre of rotation, and so this gives us the amplitudes of these complex points, the fixed points of these dynamics, and the contact points of this line with this conic. So notice from our construction that all of this thing was done just using, can be done just from an involution. Once you have an elliptic involution, you can use this semicircle method to find the centre of rotation. Once you have a centre of rotation, you can use that to find the fixed points of that involution. So essentially we can now use involutions exactly to represent complex points. They represent pairs of complex points, in fact. In fact, we can see that this is exactly what our representation of a complex point is. You see, our normal representation of our of a complex point consists of the real components and this kind of amplitude, which is sort of represented by an interval, which goes some direction at either side of our point to represent what the size of the imaginary component of that point is. Well, now we can see that this, which in this scenario corresponds to, well, this point here that I'll colour in purple, this is the real part of these complex points, and the place where these yellowish lines meet the black line, they mark out the amplitudes. But now we can see what this representation is exactly just an involution, because these places where these yellowish lines meet the point, they do so at an involution. They're at 90-degree angles to each other from this point of rotation, and the other points in involution showed in this picture are the purple points and the point at infinity. So, as I was saying, to represent an involution, or in other words, to have enough information to work out the complex fixed points, we just need 2 points together with their images under the involution. And this is precisely what we have in our representation of complex points. We have these 2 points joined with yellow lines joined to them, they're in involution, and we have this purple point together with the point at infinity, they're in involution. So what I've shown you essentially with this semicircle drawing method is how to work out the fixed points of an elliptic involution, that is, an involution which is induced in the case where the line doesn't go through the conic in question. Now, to work out these fixed points, we used one point and its image under the involution and another point under its image under the involution. Now it turns out that this same method works when we have any point A in its image A dash and another point B in its image B dash, and we can pick A in A dash and B dash to be any 4 points, and there'll be an involution that sends A to A dash and B to B dash. Now, provided that those 2 pairs, A and A dash and B dash, separate each other so that the segment between A and A dash goes through either B or B dash, and vice versa, or provided they separate each other, that will correspond to an elliptic involution, and therefore we can use this method to work out the complex fixed points. So if we just look at another example, we see how general this method is. So we take any line, and then to specify a elliptic involution on this line, all we have to do is specify a point and its image, and another point and its image. Now, provided that those 2, so let's label them just for clarity. So this is A dash, B and B dash. So provided these two pairs separate each other as they do here, with in this case B dash separating A from A dash and so forth, this will correspond to an elliptic involution induced by some conic, and we can just draw these semicircles and use this method to determine the complex fixed points of this involution. In particular, we know it corresponds to rotation about this point. So now we drop a perpendicular from this point to find the real components of these fixed points, and we can draw a circle like this, excuse me, to find 45-degree lines out of this centre of rotation, and these meet our line at these 2 points, which give us the amplitude or the size of the imaginary components of the complex fixed points of this elliptic involution. So we see that in general elliptic involutions are induced by 2 object image point pairs which separate each other. So what about the other kind of involutions? As I was saying, elliptic involutions are induced by a conic which doesn't meet the line at real points. So what are the other situations? Well, the other situation, of course, is where our line, our black line that we're thinking of dynamics upon, where that does meet the conic. In this case, a hyperbolic involution is induced. So if we have a point on the line, its image, again, to find its image we just take its polar and see where that meets the line. So this is one object and its image. Let's take another object. And its image. And so this is a so-called hyperbolic involution, and we can see that the difference here is that the object image pairs don't separate each other in the same way. It's perhaps clearer in this picture here. So we don't have this scenario that given 2 object image segments, they have one point, they overlap each other at one point. So finding the fixed points of a hyperbolic involution in this case is fairly easy. We see that it's just the contact points, the real contact points in this case, of the line and the conic. But what about more generally? Well, it turns out that more generally, such a hyperbolic involution can just be described by giving one object in its image and another object in its image, provided that those 2 pairs don't separate each other. If they separate each other, it will correspond to an elliptic involution. So how do we work out the fixed points of such a hyperbolic involution? Well, we can't use the semicircular method again, because in this case, since our object image pairs don't separate each other, of course these semicircles, they won't meet in the same way. So what do? Well, what we can do is project this scenario onto a conic, and this is fairly educational. At least it'll be educational in the long run, because in fact this method does also work for the elliptic case. But in order to apply this method in the elliptic case, which we're not going to in this video, one has to look at the kind of complex geometry analogues of all of the construction that we're about to do. So we have these two pairs here which don't separate each other, and then we draw any conic. Now this has got nothing whatsoever to do with the conics we were using to induce mappings before. What we're going to look at now instead is how we can translate these dynamics on the line onto dynamics upon a conic. So the way that we do this is we pick a point upon our conic. This is sometimes called an auxiliary conic, or sometimes called a Steiner circle, since circles are often the conics chosen. People choose circles for simplicity, and Steiner was a mathematician who helped develop this idea of when you have a sort of projectivity on a line and you want to work things out about it, often it's a good idea to project onto a conic, work out the answer there, and then project the answer back onto the line again. That's what we're going to do here to find the fixed points. So we just project via our point on the conic each of these 4 points. So this point here is projected to here. This point here is projected to here. So the left hand side green arrow on our line is projected to this orange arrow on our conic. This point's projected to here, this point's projected to here, and the right hand side green arrow on our line is projected to this orange arrow on our conic. So what we have here is two object image pairs that are on an involution which is occurring upon this conic which we've just made. So I haven't told you about how involutions work yet on a conic. Basically, the idea is that there's going to be some point on the plane, and okay, let me just shift these around a bit. We'll use it involution that's a bit easier to work with. There we go. Yes, so there'll be some point on a plane such that this involution on the conic is basically described to us by lines through that point. So if we extend out these lines here, there we go, we find that this is the point. This is sometimes called the pole of the involution on the conic. And you can set up an involution on a conic about any point. And if you want to work out, let's say we have a point on our conic here, and we want to work out what the image is under this involution, then we just join that point through our pole, and the other place where that line joining the point meets the conic, that's the image of the point. So this point gets mapped to this point, and it's an involution, so under 2 iterations every point's returned to itself. So what are the fixed points then of this involution on this conic? Well, they're if we just simply take the tangents from our pole back to the conic, the place where these tangents meet the line, they are our fixed points, simply. So that's pretty much the problem solved. We've worked out what the fixed points are of this mapping which we've moved onto the conic, and then all we have to do is move it back onto the circle again. So if we just project these fixed points back, we use the same projection point. We'll project them back onto our line again. These give us our fixed points. They are here and here. And you can sort of see that makes some kind of sense, that these 2 points will be hopping, the mapping will be hopping between these points, and somewhere between them there'll be fixed points. As I said, by projecting using a point on a conic, we can always go from an involution upon a line to an involution upon a conic, and once we've done so we can analyse it differently. And so in general then, a hyperbolic involution is going to be given by a correspondence of 2 pairs of points upon a conic. Sometimes an object and its image under an involution are called mates. So given a pair of non-overlapping mates upon a conic, that corresponds to a hyperbolic involution of the conic, and joining each point with its mate by a line, we get 2 lines. Where those 2 lines meet, that'll give us the pole of the involution. And so when the pole is outside, it's a hyperbolic involution, and we can use tangents to find fixed points and all the rest of it. Because the other case is the elliptic involution. This is corresponding to the case where the complex fixed points are imaginary, and in this case the pole of the involution lies inside, and in this case again, if we want to work out the fixed points of this mapping, we would draw tangents from this pole, see where those meet the conic, and where those tangents meet the conic, they'll be the fixed points. But you see that now this point is inside the conic, so how do we draw tangents from a point inside the conic? Well, we can't draw real lines from this point to the conic, because it's inside, but we can draw imaginary lines. And so by using the sort of theory of imaginary aspects of geometry, as I'll discuss more, we can actually complete the sort of consistent construction, and we can draw these complex lines which meet this conic tangentially from this point, and they'll meet it at complex points, and they'll be the fixed points of the system. So complex points can be represented by elliptic involutions. To do this, we just have to put two pairs of mates of points, as in object image pairs, two object image pairs that separate each other. Now, traditionally we would represent a pair of conjugate complex points by a point representing their real component. That could be, let's say, this point here, which I shall colour yellow, and then these 2 points representing the amplitudes. They're going to, in fact, those points are going to be in correspondence with each other in the corresponding involution. I'll colour those cerulean blue. And then the other point will be the point corresponding to the first one, and that's going to be off at infinity. This would be our standard representation of a complex point by the real components of the amplitudes, and this corresponds to an elliptic involution with a point at infinity and the other two points harmonically separating the point that gets mapped to infinity. But anyway, we don't need to represent the complex points like that. Just putting them in just representing them by an involution will do, because once we have the elliptic involution, we know that the fixed points of that involution will be these complex points that we're after. So now finally we can get a definition of a complex line. So complex lines are just involutions of lines, elliptic involutions of lines about a point. That's all they are. So if we just put any point on the plane, we can look at a projectivity from this involution of points on the black line to involutions of lines through this black point that we've just drawn. So let's do this. We only need 2 pairs of mates of lines. So this line here, which we shall colour in red, under our involution, this is sent to this line here, which we shall make dotted. That's the mate of our first red line. And this blue line here, this is mated with this blue dotted line. So here we have 2 lines and their mates, and you can see that these separate each other in the sense that the angle, an angle between a solid blue line and a dotted blue line goes through a red line and vice versa. So this is a elliptic involution of lines, and essentially we can think of it as a representation of a pair of conjugate imaginary lines. So all of this is really totally analogous with the setup we had before with the points. In fact, what we really have here is a kind of imaginary triangle, if you like. So we have a real line, and by this involution here, let me just move this so that's not perpendicular, less confusing. We have this real line here, and on this real line we have 2 complex points. Those complex points are the fixed points of this involution. So we just represent them by the involution itself. Now, by finding the sort of projection of this, well, it's really a perspectivity from this involution of points on the line, and changing it into an involution of lines through this point here, we essentially construct an involution of lines through this point. And just as an involution of points on a line corresponds with a pair of conjugate complex points on that line, so we also have an involution of, well, an elliptic involution, I should say, of lines through a point corresponds with a pair of complex lines through that point. So what we have here is a imaginary or complex triangle. It has two complex points on this black line, and each of those is connected to this real black point down here by imaginary lines. The two complex points are conjugate with one another, and the two complex lines are conjugate with one another. So we have here an imaginary triangle, and this is basically the method by which you can connect complex points to real points. All you do is take the involution of points, which corresponds with the complex fixed points, or take an involution which corresponds with them, and then you can just project that involution to get an involution of lines for a given point. That involution of lines can be thought of as a pair of conjugate complex lines. All of these involutions are elliptic. They're the ones which have the complex fixed points.